Do we all live in a gigantic void? What sounds like a contradiction in view of the overwhelming diversity of the starry sky is, in fact, capable of solving one of the greatest mysteries of modern space research. While the observed value of the Hubble constant simply does not match our theoretical models, the so-called Hubble tension could be explained by the fact that the Earth is located in a kind of underdense bubble in space. But although this groundbreaking approach finally provides a solution to the discrepancy in the measured values, it also leads directly to a new research dilemma. According to our understanding, such voids in the cosmos simply should not exist. The question of how fast the universe is actually expanding may seem simple at first glance, but in truth, it is one of the greatest mysteries of contemporary research. On the other hand, it has long been one of the basic facts of astronomy that the cosmos has been expanding incessantly since its birth about 13.8 billion years ago. For a better understanding, however, it should be noted at this point that the universe is not expanding into an existing space. No, it's rather space itself that is continuously expanding. As the universe expands, the individual galaxies also move away from each other, and it should be noted at a speed that is proportional to the distance between the galactic worlds. This means that if Galaxy A is twice as far from Earth as Galaxy B, its distance from us also increases twice as fast. But to decipher how fast two galaxies move away from each other in detail, we not only need to know their distance, we also need a factor by which we can multiply this distance, and this is precisely where the Hubble constant comes into play, a parameter in Einstein's field equations that, contrary to its name, is not a constant at all since it is only constant in space but not in time. There are basically two different ways to determine the corresponding value of the Hubble constant and thus the current rate of expansion of the cosmos. On the one hand, there is the possibility of determining it with the help of the cosmic background radiation, that is, with the microwave radiation relic that dates from the period shortly after the Big Bang and still fills the entire universe today. So when researchers measure the cosmic background radiation and combine it with the theoretical models of cosmic development, they arrive at a current expansion speed of 67 km per second per megaparsec. The crucial problem, however, is that the actual measured values for the Hubble constant deviate drastically from the theoretical predictions and are significantly higher. In other words, if the distance measurement is based on supernovae, red giants, gravitational lenses, and variable stars, we are confronted with a Hubble constant that suddenly amounts to 73 km per second per megaparsec. Now, a difference of 6 km may not sound like much at first glance, but this changes abruptly when we consider that the expansion rate increases from 244,000 km per hour per megaparsec to 264,000 km per hour per megaparsec. Conversely, this means nothing other than that the universe is expanding 20,000 km per hour faster today than it should be according to the cosmological standard model. But how is that even possible? Have we misunderstood the universe? Well, the simplest explanation would be that the astronomical devil of error has crept in. According to this, a combination of measurement errors and inaccuracies in the past could have led us to now having a research puzzle that is not really a puzzle at all. To check this, Adam Rees and his team used the James Webb telescope to analyze over 320 Cepheids in several galaxies, many of which had also been previously examined by the Hubble Space Telescope. And if anyone is familiar with this topic, it's Adam Rees. After all, the American was awarded the Nobel Prize in Physics in 2011 for discovering the accelerated expansion of the universe through distant supernovae. In the case of the most recent research study, however, Rees had a different insight. Webb should confirm the Hubble tension again. The new data also show a Hubble constant that is significantly higher than that obtained from the theoretically derived models. Fortunately, Rees also immediately knew an explanation for this puzzling deviation. It could be that we have simply misunderstood the universe. Perhaps we have overlooked something in our understanding of the cosmos, an unknown force that has not been taken into account in the cosmological standard model. This could be a new type of particle or an erroneous conception of gravity. Furthermore, it is conceivable that there is an exotic form of dark matter or dark energy out there that is currently completely unknown to us. Just a brief reminder, neither dark matter nor dark energy has yet been directly detected. They are therefore purely hypothetical forms of matter and energy that were postulated to explain the motion of visible matter on the one hand and the accelerated expansion of the universe on the other, where Einstein's theories falter. While Adam Rees openly refers to the possible ignorance of the astronomical research community, another team believes that they have finally solved the tantalizing riddle of the Hubble constant. The study presenting the novel solution was published in the journal Monthly Notices of the Royal Astronomical Society, and its quintessence can be summarized as follows: we live in a vast void in space. But what does that mean? After all, the starry sky, with its thousands and thousands of objects, is not exactly what you would call empty. Well, what is meant is not a starless night sky but the assumption that our Earth is located in a region of space where there is relatively little matter. In the corresponding press release published by the international research team for their study, the cosmic void is compared to an air bubble in a cake for illustrative purposes. Since the density of matter outside the sparsely populated bubble is consequently higher, the gravitational forces there pull the galaxies inside the bubble towards the edge of the void, and faster than would actually be expected. This would explain why the cosmos seems to expand faster near us, or in other words, up to a distance of about 3 billion light-years, than in its entirety. The existence of regions with below-average density is therefore able to eliminate this contradiction to the standard model of cosmology. But unfortunately, it simultaneously raises a completely different problem. In fact, the standard model does not provide for such underdensities at all. They should not exist at all since matter in the universe should actually be evenly distributed. And yet, there is a way to get around this new contradiction as well, but this requires saying goodbye to Einstein's theory of the nature of gravity. According to this, it is possible that gravitational forces ultimately behave differently than Einstein expected. In reality, this theory has been around for some time. For their study, the researchers relied on a modified theory of gravity that the Israeli physicist Mordechai Milgram had proposed as early as 1983. This so-called modified Newtonian dynamics, or MOND for short, explains the rotational behavior of galaxies by modifying the equations of motion of matter in the gravitational field. Accordingly, this hypothesis is also considered an alternative to dark matter. However, it's still the subject of heated debate and has not yet advanced beyond the status of an outsider theory. And yet, and this is the crucial point for the study authors, MOND accurately predicts the existence of underdense bubbles in space. If gravity really does behave according to Milgram's ideas, the problem of the Hubble tension would have disappeared from one moment to the next, and one of the greatest mysteries in cosmology would finally be solved. Or is there no Hubble tension at all? Well, if Wendy Friedman has her way, then despite all new studies and observations, we could ultimately be dealing with problems that don't really exist. To understand what is meant by this, we have to briefly go back to Adam Rees's research study. In this regard, the Canadian astronomer suspects that dust, gas, and the effects of other stars can fundamentally distort the brightness measurements of Cepheids. This is because Cepheids are mainly found in the disks of galaxies, where the stars are sometimes so close together that their light overlaps for a distant observer. To test their hypothesis, Friedman and her team examined 10 nearby galaxies with the James Webb telescope, which, in addition to Cepheids, also contain two other distance indicators. On the one hand, there are red giants that are about to start burning helium in their cores. At this stage, the celestial bodies reach an intrinsic brightness that is more or less independent of their composition and history. The comparison with the apparent brightness therefore allows conclusions to be drawn about their distance. The situation is quite similar for the other stars examined, which are further along in their development.
There are red giants that are about to start burning helium in their cores.
The analysis, which took several years, came to the conclusion that the distances measured using the two new methods are in very good agreement with each other and that they all yield greater distances than those determined on the basis of Cepheids. Consequently, it is conceivable that the Hubble tension is, in fact, due to the fact that we have calibrated the cosmic distance ladder incorrectly. Specifically, Cepheids are used to determine the lowest rungs of the distance ladder. However, if the lowest rung already contains a systematic error that consequently runs through each subsequent rung, the value of the Hubble constant will inevitably be distorted. However, we currently do not know where exactly these errors lie and whether they really exist at all. In fact, Adam Rees emphasizes that the Webb data he has collected explicitly rules out the possibility that systematic measurement errors or inaccuracies caused by the light of neighboring stars have played a decisive role. But now you can play the decisive role of a new subscriber. Please click on the thumbs up and on the subscription button so you never miss a new video from us again.